Remember that an artificial neural network, or ANN, is composed of neurons, which we're going to represent as circles, and synapses, which connect neurons together and cause one neuron to influence another. Neurons have values, and synapses have weights, which influence the weight of the influence of one neuron on another. To calculate the values of neurons that have incoming edges, we multiply the value of the connecting neuron times the weight of the synapse that connects the neurons together. If the value of a neuron changes because of some external event, like sensory stimulation, we recalculate the new values of the internal neuron by again multiplying the value of the sensor neuron times the weight of the synaptic connection between them. Let's imagine that we have two sensor neurons now that collect information from the outside world, and both of them influence our internal neuron. Let's imagine that the first sensor neuron inhibits the internal neuron, and the second sensor neuron excites our internal neuron. If we now update the values of these two sensor neurons to reflect what they're sensing from the real world, in this case, to compute the value of the internal neuron, we sum the influences of the first sensor neuron on it with the influence of the second sensor neuron on it. Let's imagine now that we have a total of n neurons which are influencing our internal neuron, which we'll now refer to as neuron I. We'll now represent the weight of influence of neuron 1 on neuron I as Wi1, and the weight of influence of neuron n on neuron I as Win. We can represent this mathematically as follows. We can write down that the activation of neuron I is equal to the sum over all of the n neurons that influence it, where the influence of any given incoming jth neuron is equal to the weight of the connection from neuron j to neuron I multiplied by the activation of the incoming neuron j. We usually wish to keep the range of values of our neurons within some desired range, which in this project is between 0 and 1. So sometimes, as you can see in this example, we'll obtain a new value for our neuron which lies outside of this range. In order to keep the values of our neurons within the desired range, we'll often apply a squashing function, here represented as sigma, to keep neurons within this valid range. In this case, the function we're going to use is a thresholding function. If we compute the sum and it's below -1, we'll set the new value of the neuron to -1. If the sum is above +1, we'll set the new value of the neuron to +1. If it's neither of these cases, we'll just set the neuron normally.